Welcome. Today we're going to start a new course in data science. Although the title says Introduction, this is a serious course. More of a broad overview of data science. We assume that you have taken a good number of computer science courses to understand some of the technical details that we will cover in this course. So let's start. So I'll go over some of the topics such as what's data science and so on. And let's start with the definition. What is data science? So obviously the word says data. It involves a lot of data, the big data, and also science. Science means that something that we can create that's repeatable. So it's really the application of computational and statistical techniques to address or gain insights into problems in the real world. We collect the data from the real world and then we try to solve them. So the process goes like this. So we have a reality. As a result, we collect some raw data. And the data has to be processed because data is always messy. And then we clean the data sets. And then we explore the data set using charts and other things. Once we are happy, we will create models and algorithms and communicate that to the world. And then eventually your goal is to take this model, integrate into a data product, and perhaps market it to the world so that reality can be tested using this model. So data science, why now? We are collecting and storing a lot of data. For example, Google processes more than 20 petabytes of data every day. That's around 3.5 billion search queries and 44 zettabytes of data in the world in 2020. A zettabyte is 10 to the power 21, which is a fairly large number. We have better and faster machines, such as, obviously, we had CPUs. Now we have GPUs, the graphical processing units, as well as TPUs, the tensor processing units. We have better machine learning algorithms, such as deep learning with neural networks. So it's hard to argue that data is the best way to understand problems and find solutions. So need for data scientists is real. Data scientists will become the most in-demand profession in the next 5 years, according to scientists and analysts. This is from a 2021 article. And some of the best jobs in the US, according to Glassdoor, data scientist number 3. And you can see that. Just go to Glassdoor and search for data science jobs. You will find tons of them. So when we talk about data science jobs, there are lots of data science jobs available. Data architect, strategist, governance, data modeler, big data engineers. So these are all very specialized fields of jobs that one can get by understanding data science as a whole. Now more jobs like big data architect, big data operations, database operations, data Q&A, and data analyst. So, R. Hamming, many years ago, 62, said that the purpose of computing is insights, not numbers. We get numbers from data, but we have to generate insights from those numbers. So, right now, the skills for the 21st century involves that you have to understand, every human needs to understand how to work with big data or program a computer, regardless of whether you're a computer science major or not. Data science is interdisciplinary. For example, it contains math and statistics and expertise and hacking skills. So, for example, as a computer science person, you might have a lot of hacking skills. And then if you combine the hacking skills or CS with math, you create the field called machine learning. And then math and statistics with some expertise create traditional research. And if you have hacking skills and expertise but don't have the math and statistics, that's a danger zone because you don't have the foundational theory that's necessary to be careful when you're writing models. So data science is really the cross between all of it. So it's very interesting and timely. So as we all know, the statistics is the science of collecting, classifying data, linear algebra, the mathematics of matrices and vector spaces, because all the data are stored in some form of a structure like a matrix or vector. AI is the study of computer algorithms, dealing with simulation of intelligent behaviors and so on. Then the machine learning is the study of computer algorithms to learn in order to improve automatically through experience. So databases, the science and technology of collecting, storing, managing data. So users can retrieve, add, update, remove such data. As well as data warehousing, the science and technology of collecting, storing, managing data with advanced multidimensional reporting services in support, and so on. So if you ask the question, which of the following courses have you taken or currently taking, I will have to assume that you have taken a course in linear algebra, you have taken a course in statistics and probability, or have a good understanding of these two things. You don't need to have an understanding in machine learning or AI to take this class, and we will visit some of those topics during the duration of this course. The other question you can ask is that, in your opinion, which of the following branches of mathematics likely to be the most important to data science? It turns out that linear algebra is one of the most important areas of data science, and optimization, which is minimization of loss and maximization of the outcome, are very important. Multivariate calculus can be important. Probability can be important, and statistics can be important. So you need to have a good understanding of all of these things. So let's take a look at what we do. Data science explain the past. Explaining the past means use the existing data to understand the phenomena. So explaining the past means that you exploit, whether in a univariate, one variable, or multivariable, and the data can be put into categorical and numerical, and within those you can look at various things like statistical things, max, mean, median, and so on. So this is really looking at the past. But a data scientist is about predicting the future. So we have to create a model to the data to predict the future. So predicting the future involved some level of modeling of the data using classification principles or regression or clustering or association rules. So what's the difference between data science and computer science? So in traditional programming, we provide the data and a program written by a human to a computer. And the computer provides an output, such as finding the square root of a number. So in this case, we can test with the data, but we write the program. The human writes the program. In machine learning, this is kind of reversed. We know what the data is, we know what the expected output is, and we want to write a program to find the right program. So the program is produced by the machine, not by the human. In this case, it's the human, now it's the machine. So here, for example, you can assume that our data could be a picture. Our output is we expect that picture to be some kind of an animal, cat or dog. Your program will be able to correctly classify that as a picture of a dog or a picture of a cat with certain level of uncertainty. And our goal in data science and machine learning is to minimize that uncertainty. Okay, so those who have come from a computer science background and take a data science, and I like to call them computational data scientists. They understand the big data systems and the big data algorithms, and also the complexity of the computation you're going to be doing. So you're just more than just a data scientist, you're a computational data scientist. It's going to pay attention to a lot of the details. So data science is not machine learning, although machine learning is used in data science. It's not competitions like Kaggle, goal is not optimizing it for a given data set, but for really generalizing it for the most part. It's not statistics, although statistics forms the foundation for this. It's not about big data. You don't always need massive amount of data to answer the questions. It's mathematics. The linear algebra is important, but only one part of data science. So next, let's take a look at some of the data science applications in the real world. Let's think about job description. Your boss says that we need a big data system that will replace our classical services in order to provide a more personalized system. You would say, sure, it sounds like a good idea, let's do it. But the boss says, wait, it should work well for everyone. The company can tolerate a few errors, but not too many to embarrass the company. You will say, okay, that's fine. We can go through testing to make sure that's the case. Okay, but it should run as fast as our classical service or even better. That sounds complicated. Personalization is the goal, requires more resources and processing, but we can try. As we collect more data, it should not slow down. In fact, it should improve the service. Now, so that's the tough question now. So how do we deal with that? So let's take a look at some of the questions that might involve, if you're looking for a job, an interview question. Suppose you have two tables, Excel, SQL database tables. One table is publisher information, which contains ID, video duration, and the other one is the user information, user ID, the video that the user has watched, and the user time spent. Now, if you ask the question, how many minutes worth of videos the average publisher have, you can just take that information from this table alone. We can look at the total number of video lengths, because we have the video generation and you have the publishers, and you can figure that out. And then the question two would be, how many publishers have at least one user who watch their videos? In this case, you have to combine these two data sets using a common video ID to figure out what the answer to that question is. So we will not answer that question, but that's the kind of question that you might run into. So here's another kind of question that a company sells an over-the-counter test kit that's advertised to be 99% accurate. That means if you have the disease, you will test positive 99% of the time. If you don't have the disease, you will test negative 99% of the time. And it's known that 1% of the population have the disease. The question is, what's the probability that you have the disease if you tested positive? So the key thing is that we are going to use conditional probability to answer this question. For example, given that you tested positive, what's the probability that you have the disease? So we can construct that using statistical things. The other question might be, you're working for an app company and the company wants to know how to introduce a share video feature. The video can be shared with followers or friends. How would you design an experiment to know whether to launch the feature or not? The questions like what data and how would you collect them? What's your success matrix? So these are important things to think about when you think about data science. So where are the data science opportunities? Really, the high-paying, high-qualification opportunities are at the top. AI deep learning engineers, A/B testing, experimentation, machine learning, analytics, and so on. At the lower level, there are many more jobs of collecting data, instrumentation, logging, sensors, user-generated content, and also figuring out the reliable data flows, pipeline, structured and unstructured data storage, and so on. So there are many more jobs here, but they don't really require, some of them don't require a college degree. But here you need highly specialized college degrees, and they're also high-paying jobs. So for questions data scientists might be interested in are the heights, weights increasing in the population. Where should we put docking ports for our bikes? Do left-handed people have shorter lifespans than right-handed? So these are just questions that we are asking, and these questions can be answered by collecting data. We're not trying to predict anything, but we're trying to see if there's a trend that the heights and weights in general are increasing in the population. So challenges in big data is the analysis, which requires computational thinking and inferential thinking. And computational thinking is really the abstraction, modularity, scalability, and robustness. So a lot of computational thinking which you develop as a computer scientist can be very helpful. Inferential thinking is that real-world phenomena are behind data. So sampling patterns that can give rise to the data and the backward procedures from the data to the phenomenon. That's the modeling part. So data science life cycle involve asking a question, obtaining the data, and understanding the data, and then you keep obtaining the data until you can understand the data, or you keep asking the question and obtain the data, understand the data, and then through that data understand the world. Once you understand the world, you can create reports and decisions and solutions. So one of the questions we can ask here is that, are there more males than females enrolled in CS 439 in a course in data science? You can answer this question by collecting the enrollment data. And one of the problems that you will run up here would be that typically you don't have the gender information in the university rosters. So you'll have to infer the gender from the roster itself, the name itself. So perhaps the first name might be a reasonable way to infer the person's gender. You don't have to be 100% correct. And as long as you can extract that information, you can answer that question. So there are also obstacles to get this data, for example, privacy and other issues that institutions protect data. So obtaining data is not that simple, especially if you're trying to answer a question. And understanding the data is, how do we know the gender of people by name only? Like if you look at the first name, can you know the gender? It may not be correct all the time, but if it's correct 80% of the time, I think we can live with that. All right, so in this course, we're going to learn techniques that make data speak in order to create persuasive narratives and arguments about the world. Data science stories are particularly powerful. Data science makes claims about the real world. People place a lot of trust in science and scientists, and it's often difficult for others to scrutinize data or verify the dispute claims. So there are two distinct entries into this data science lifecycle. For example, you can start by formulating a question, or you can start by just acquiring data and cleaning them and then try to come up with the question. So you can ask the question first, collect the data, or you can collect the data, then ask the question, and then go through this data science lifecycle. So in asking the question, we want to know what problems are we trying to solve, what are the hypotheses we want to test, and so on. In terms of data collection, acquisition, what data do we have, what data do we need, how will we collect more data, and how do we organize the data for analysis. And in the area called exploratory data analysis, or EDA, and visualization, we can always look at the data we already have, look at our data in graphs form, get a subset of the data, and do the analysis. And then finally draw conclusions and predictions and inferences. So here's another way to look at data science lifecycle. We can have the data. So this is a never-ending cycle because you just have to keep processing data to improve your model. So question, just pause a little bit and think of a situation or problem you're familiar with and identify what you would do in each of the steps in data science lifecycle. Okay, in terms of interpretation of data, so you can look at various graphs to see that this is from gendered language and teacher reviews, and are females more funny than males, and so on. So, so depending on the area of computer science or something, so you can make certain inferences. So forecasting, for example, the race for the house, so this graph could give you various information about things. Poverty mapping would require, for example, collecting GPS data and income in those areas and then plotting them to see which areas have the highest poverty. So we can infer a lot of things from data visualization, and various graphs are shown here. Correlation or causation, this always comes. For example, people who died by falling out of wheelchair highly correlates with the cost of 16-ounce potato chips. And so, but we know that this has no causation, but so you have to be very careful about correlation and causation. And if you ask the question, where do you want to live? New York, Virginia, Florida, then you can get all this data from various sources, and then you can model it and see which state gives you the right kind of things, because there are lots of variables that you want to look at when you make a decision to live in a particular state. So if you look at another question like this, what's wrong with this interpretation? Because it looks like the abortions have gone up fairly high while the cancer screenings are going down. But if you pay attention to the scaling of this graph, you can see that the percentage-wise, the cancer screening have gone down, but as a percentage, abortion have gone up. But look what's the percentage of up. So you can make a decision just by looking, not by looking at the data, but also paying attention to these numbers. Okay, there are some tools for working with big data, for example, TensorFlow, Apache Spark, and other kinds of things. And you have TPUs and some accelerated computings, clusters of CPUs, clusters of GPUs, and so on. That's all available for you now. So next we will take a look at the other sides of data.